Okay, welcome back. Before I dive into this stuff right here, I want to just do a quick little recap reminding us how to calculate or find a union or intersection of two sets. So let's say I've got one set over here that contains the elements 1, 2, 3, 4, 5, and 6. Let's say I've got another set that contains the elements, how about 4, 5, 6, 7, and 8. One way to visualize these things is to think of them in terms of a Venn diagram. Now, this could be set A, so it would contain the numbers 1, 2, 3, 4, 5, and 6. I'm going to draw a bubble for set B that's going to contain all these numbers, but if you notice, there is a little bit of overlap between the two sets, right? They share these numbers in common. So I don't want to have two separate bubbles because they've got something in common. These would actually overlap. This could be set B. And in set A, I've got to have the numbers 1, 2, 3, but I'm going to put the 4, 5, and 6 here so that they are also living inside the B bubble, which should contain 4, 5, 6, as well as 7 and 8. But they are outside of the A bubble. All right, so again, it's like we're writing these two sets together, but we're indicating the overlap, and we're not writing them out twice. So I can do two things here. One is I could find the union of these two sets, or I could find the intersection. Now, a union is synonymous with an or. Whoa, whoa, whoa. What'd you do to me? No, okay. All right, let me come back. I want the union of these two sets or the intersection. Okay. Again, when you hear of an or statement in probability, we are talking about taking the union, and we're going to see a formula for this in just a little bit. If I want the union of two sets, we indicate that A union B. That's the symbol for union. And what the union is it literally means I'm basically gluing these sets together. I'm taking everything that's in A, and I'm also going to include everything that's in B. I'm going to mash the two sets together, but I'm not going to double count anything. So anything that's got some overlap, I'm not going to list it twice. The union of these two sets would be just putting them together. So I've got 1, 2, 3, 4, 5, 6, 7, and an 8. Okay. Now the intersection of these two sets, on the other hand, is synonymous with an AND statement. And I would write it A intersect B. That's the symbol for intersection. And what the intersection looks for is it looks for just the overlap of the two sets, right? Just what they have in common. So there's set A. Oops. Whoop, didn't mean to do that. There's set A. I'm just trying to erase that little bit there, or the whole thing. And if I were to find the intersection of that with set B, look what happens. The intersection is shown right there where the thing turned green. That's the intersection. Right? Where the bubble turned green, that's the overlap of the yellow and the blue. The intersection is asking for exactly that set. Where do A and B exist at the same time? Well, those would be the elements 4, 5, and 6. That would be the intersection. If you want more help or, kind of need help reminding or remembering how to work with unions and intersections, let me know. I can make up some other problems. But let's see how they apply to probability. Where they're going to come into play in probability is that now we're not going to be finding the probability of just one event. There's going to be maybe more than one event, and we are going to look for the union or intersection of those two things and find the likelihood of them happening. So again, the rules of the game are changing. Sample space gets harder. All these things are what make probability a little more challenging. Here's the scenario. We're rolling a 6-sided die, and A and B represent the following events. So A is the event that I roll a number greater than or equal to 4. B is the event that I roll an odd number. Okay, so again, I'm rolling a die. All right, so if I'm rolling a die, everything that could happen is I could roll a 1, 2, 3, 4, 5, or 6. Those are my options, right? Okay, So let's take a look at a Venn diagram of these two events. I've got event A here. This is me rolling a number greater than or equal to 4. Okay. Now, before I draw this, I kind of have a question. Should I draw it like this, or should I draw it overlapped? Let's look at the two events. If I'm going to roll a number greater than or equal to 4, that means I could be talking about U, or U. Those are all the numbers greater than or equal to 4. Is there any overlap with this set? There is, right? Because event B is asking what's the likelihood that I roll an odd number. Well, there is an odd number in that set. So when I draw this Venn diagram, there's overlap between the two of them. What they share in the middle, what number belongs to both event A and event B is 5. Because 5 is a number greater than or equal to 4, so it belongs in the A bubble. But 5 is also an odd number, so it belongs in the B bubble. Numbers that belong in the A bubble only would also be 4 and 6, because those are numbers greater than or equal to 4. And numbers that belong in the B bubble only, but not in A, would be all the other odd numbers, so a 1 and a 3. And there's one number that doesn't live in either of these two events, and we indicate that by writing it outside of those bubbles here. So I've got every outcome shown, 1, 2, 3, 4, 5, or 6, and I've also kind of dissected it and laid it out so I could see which numbers land in event B, which numbers land in event A, and which numbers land in the intersection of the two that occur in both of those two events. So they are asking me for the probability of A or B. That is a union, right? So remember, the OR statement is when we should think of union. So when I roll a die, again, we're still doing probability. So probability is just the number of ways to pull off a success. How do I achieve this? Divided by how many total possible outcomes are there. When you roll a die, there's 6 possible outcomes. Okay. I want to know how many of those numbers land here in this union, right? However many numbers land in this union, that's the number of ways I can pull off a success. Well, remember, a union just glues them together. If you're in one, you're in the union. So there are 1, 2, 3, 4, 5 numbers inside the union. So the probability of A or B would be 5 out of 6. Be it. Okay. Now we're going to look at the probability of an intersection. Same two events, same scenario. I'm rolling a die, right? So the outcomes are 1 through 6, same two events. But let's look at their intersection here. And again, it's an intersection because they're asking for the probability of A and B, meaning they both have to happen simultaneously. My Venn diagram is going to look exactly the same. I've got event A and event B, and they share a 5, and event A has 4, 6, and 1 and 3. And nobody has event 2, or 2 does not belong to either of those events. So if I want the probability of A and B, right, that means I need to find, well, out of 6 possible outcomes, right, because I could roll 6 possible numbers here, I need to know how many fall in this category. This would be a success for me. So how many of them land right here? Well, there's only one that lands in that intersection. It's the 5. So there's only 1 out of 6 ways to get a number that occurs in both of those two events. Okay, let's get some practice problems that have a little bit more meat to them, or a little more substantial. Okay, so let's try this one. It says 20 children go to the park. 5 of them bring only a kite, 8 of them bring a bicycle, and of those 8, 3 of them brought both a kite and a bicycle. So first they say, draw a Venn diagram to represent this situation. Like a sample space, a Venn diagram can be very helpful. I mean, it's just a visual sample space, and it actually helps lay out where there's overlap. So a Venn diagram is not a bad idea for many of these problems. So let's see. I've got two scenarios. I've got kids that brought a kite. I'm going to make that a little bigger. I've got kids that brought a bike. And now, is there any overlap there? Do we have any kids, kite? Do we have any kids that brought both a kite and a bike? And it says, yeah, they are. There's 3 kids that did that. So I've drawn the kite bubble to hold all those kids. When I draw the bike bubble to hold all those kids, I'm going to draw it with some overlap because there's 3 kids that belong in both bubbles. All right. So let's try and fill this in. Let's see. 5 kids bring only a kite. So there should be 5 kids in the kite bubble that do not belong in the bicycle bubble as well. It says 8 kids bring a bicycle. So this whole bicycle bubble here must contain 8 kids in total. And it says of the 8 kids living in this bubble, 3 of them also brought a kite. So of the 8 kids in this bubble, 3 belong here, where they are in the kite bubble as well as the bicycle bubble. And since this whole bubble here had to contain 8 kids, and I've already got 3 accounted for, that means there must be 5 more kids that brought only a bicycle. Again, that way there's a total of 8 kids that have a bike. 3 of them also brought a kite. Now it said 20 kids go to the park. This is not 20, this is 13 kids. So that means there's 7 kids outside of these bubbles. That means they went to the park, but they did not bring a bicycle. They did not bring a kite. Once you get a Venn diagram drawn out, just like once we had the sample space drawn out, it becomes much easier to do these probability questions. So it says, what's the probability that a child chosen at random brought both a kite and a bicycle? I want the probability of kite and bicycle or bike. Well, that's and. Again, that's an intersection. Or symbolically, we would write it that way. So how many outcomes are there in total? Again, probability is number of ways to pull off a win or a success at this thing divided by the total possible number of outcomes. There's 20 outcomes because there's 20 kids that went to the park. And of those 20, how many brought a kite and a bike? That would just be 3 of them. So 3 out of 20 is the probability that if you chose a child at random, that they would be one that brought a kite or a bike. And if you wanted that as a decimal or you'd get 0.15 or 15% chance. All right, so let's try this last one. It says, what is the probability that a child chosen at random brought either a kite or a bike? Probability of kite or bike. Okay. Again, there's 20 possible kids you might select from, right? If you're picking a child at random, there's 20 of them that could be chosen. How many of them fall in this category, kite or bike? Well, that would be 5 plus 3 plus 5. A total of 13 kids belong in either of those 2 bubbles. So 13 out of 20 would be the probability of getting one or the other, kite or bike. If you put that as a decimal, you get 0.65 or 65%. Okay, talked a lot on this one. I'm going to end this one and make a new video. See you in a minute.